In this video, I'd like to show you how to solve a particular class of differential equations using a method called the integrating factor method. This type of differential equation is of the form, can be rewritten in this form, where we have the operator dy dx plus some function, this time just of x, so a rule that has just x's, whatever it may be, times a singular y. And that's equal to a rule that, again, just involves x's. So px and py are functions or rules that only are involving the variable x. And then this one term here happens to have is multiplied by y. These classes are not always separable, but if there exists a certain function called an integrating factor, then it can be possible to solve these sorts of differential equations. I'd like to walk you through something that our kind of the typing that our textbook has, so we have some background as to what the heck's going on or where this crazy factor comes from, and then we'll focus our efforts on solving a couple examples. Note that we're not positive that a function like this exists, but if, let's say, for example, that it does exist a function that has this very important property, that if you were to take this function or this value I of x, and if you were to multiply it to both sides of our original form here, then you'd get an expression that looks like this. I times dy dx is equal to that same function times this function of x p times y, and that would equal the integrating factor. We also want this function to have this property that if you were to take its derivative times y, then after you're done with the product rule, that you end up getting the expression that would end up on the left-hand side. So this is a big if this were to exist, but in the cases where it does, and we're going to see what those cases look like, in the cases that it does exist, this is going to yield a differential equation that we can solve. Note that if it does work, then you could take the integral of the left side, the integral of the right side of this, and you'd have an expression where the integral and the derivative are inverses and kind of cancel each other out in a sense, undo each other, and you'd be left with whatever that function you came up with times y is equal to the integral of the right-hand side. This is nice because then you could just divide by whatever this rule is in terms of x and get y by itself, and thus we'll have solved this differential equation. So the real important part, so the real tricky part is, well, okay, so if it were to exist, it would have this nice property. That's great. What is this function, or how can we actually calculate what this rule would be? Well, if we come back to the property that we want it to have, where the derivative, if we take the derivative of this weird function times y, and that should be equal to what we started with on the left-hand side. If we find the derivative of ix times y, well, using the product rule, an implicit differentiation, we get the following. We'd get I times whatever the derivative of y is, which is dy dx. And then we'd have y times the derivative of this, whatever the derivative of this function in terms of x is, so I prime. And again, we want this function, we've chosen this function in such a way such that it is equal to the right-hand side of this function, ix dy dx plus ix times px times y. Note that on both sides of this equation is an ix times dy dx and ix times dy dx. And we'd be left with I prime times y is equal to this rule I times p of x times y. Further, note that what's left over each has a y, so we could divide each of these expressions by y and eliminate them, and we're left with the derivative of I is equal to I times whatever this I times p of x, which again was whatever this expression was that started in front of y. So rearranging, I divide both sides by what this function is, and we have I prime over I is equal to p of x. If I integrate both sides, well, let's see. This is you could think of this as like a u substitution. If you say u is I of x, then du is just, well, the derivative of I. So this really has the structure of the integral of 1 over u is equal to the integral of p to the x. Or better yet, the natural log of u, which is the natural log of this function I, plus c, is equal to the antiderivative of, or the integral of, whatever this function p was that we started with. And using our common trick that we've been using for separable differential equations, raise everything to a power, make everything an exponent in the exponent of e. And we'll end up with getting I alone. We'll have e to whatever the integral of this function of p is. And then there'll be some constant of integration. And by convention, usually this constant of integration is taken to be 1 for simplicity's sake. Put all this together, and it turns out that for differential equations of this type, again, for differential equations of the type dy dx plus some function of x times y, and this equals some other function of x. For this type, the integrating factor, multiplying through by this integrating factor, of e to whatever the antiderivative of p to the x is. Multiply everything through by this, and what will always happen, and what's nice, will always happen is that you can recognize that the left-hand side will become the derivative of this integrating factor times y. And the right-hand side will just be, well, the integrating factor times what we start with. And from here we can always solve this differential equation by integrating both sides and getting y by itself. So I'm going to use this idea, and I'm going to solve a couple example problems for us. Okay. The first, here's a differential equation, dy dx plus 3x squared y equals 6x squared. I'm recognize that in this case, this is in that form that we talked about. We went dy dx plus some function of x times y equals some other function of x. I'm going to recognize that my p to the x in this case is this function of x that's multiplied to y, which is 3x squared. And then the q of x is just 6x squared. It's not nearly as important or useful as what this p to the x is. So what does this tell us? It tells us that our integrating factor then, this means that our integrating factor is e to the antiderivative of 3x squared. The antiderivative of 3x squared is x cubed. So the thing I want to multiply through this entire equation through by is e to the x cubed. So I do that. I multiply every term by e to the x cubed. That gives me e to the x cubed dy dx plus e to the x cubed 3x squared y. That equals e to the x cubed 6x squared. The reason we chose to do it, we chose this method is that we can recognize that the right-hand side is better known as the derivative of this integrating factor times y. And you can show, if you're not convinced, you can, well, find the derivative of this, use the product rule, and what do you know? You'll end up getting what's on the left-hand side here. So let's use what we know here. And because of this consequence, we know that the derivative of the derivative with respect to x of e to the x cubed y is equal to e to the x cubed times 6x squared. I'll undo this derivative operator with an integral. The integral of a derivative is just, well, the function that we start with, ex cubed times y. On the right-hand side, and that's a 6. On the right-hand side, what's the integral of e to the x cubed times 6x squared? Well, we can find we see a quick u substitution. If we let u equals x cubed, we know that du is 3x squared dx. Or maybe 2 du's is equal to, so 2 du's is equal to 6x squared dx. So the integral of this should be, or the antiderivative of this should be 2e to the x cubed plus c. Therefore, I can get at y by itself by dividing everything by e to the x cubed. Everything by e to the x cubed. And I find that a general solution to this differential equation is, well, let's see, 2 times e to the x cubed divided by e to the x cubed is just 2, plus some constant of integration over e to the x cubed. Or maybe if you don't like e to the x cubed in the denominator, you could say this is y is equal to 2 plus some constant times e to the minus x cubed. I have one more example. Here's a differential equation that is not currently set up in that form that we discussed we would like to see. However, we can, with some rearranging and some algebra, we can get it into the form of dy dx, and then y times a function of x, and then is equal to some function of x. We're going to both solve this generally, and then we're going to use this initial condition to find a particular solution. So let's see, I'm going to start by rearranging this so that the dy dx and the term with a y is on the same side. And I may omit the of x's here because it's a pain in the butt to write. Minus y sine equals sine 2x. I divide through everything by cosine. And I get this differential equation that is in the integrating factor method form. Dy dx minus y sine divided by cosine is tangent. And cosine 2x divided by sine 2x divided by cosine x. Let's see. A quick, I remember sine of 2x actually is 2 sines cosines. Cosine and cosine will cancel, and I'll get 2 sine of x. This differential equation is in the form that I wanted to see. Further, further, I recognize that in this case, for this integrating method, that my integrating factor should be e to the integral of p to the x, and my p to the x is, I can think of, is tangent. Or maybe more probably minus tangent. So I can make this plus negative. So we need to figure out what is e to the integral of this of p to the x, or e to the integral or the antiderivative minus tangent, or minus the integral of tangent. Integral of tangent is not a standard. Antiderivative. You may recognize it from a previous course. If not, we can figure it out on the fly. This is the antiderivative of sine over cosine. If we let u be cosine, then if u is cosine, this is a u substitution, then du is minus sine. So this is really of the form minus integral of 1 over u. This integrating factor is really e to the minus negative 1 over u, or e to the natural log of u, and u was cosine. And what do you know? E to the natural log of something is just that factor. So it turns out that even though initially this integrating factor has this very awkward and seemingly complex form, many times when we evaluate it, it actually can turn into something that's not so bad. In this case, the integrating factor is simply the function cosine. So what am I going to do? I'm going to take this integrating factor cosine and multiply it back through our original function. I can do that, but it turns out that if you recall, we initially started by dividing everything by cosine. So multiplying through by cosine again is just going to get us back to where we started. In fact, we're going to get the initial. You can quite literally undo everything that we just did and arrive back at the original writing of this prior to dividing by cosine. So y minus y sine x equals sine 2x. The reason we checked for this integrating factor is that it means that what this tells us is that the left-hand side can be rewritten as the derivative of the integrating factor times y. And that should be equal to what we got when we multiplied 2 sine x times cosine, which is, well, again, what we start with, sine of 2x. Integrate both sides to undo this derivative operator. We get cosine x times y is equal to, let's see, the antiderivative of sine 2x is minus cosine of 2x over 2 plus a constant of integration. It's probably best at this stage, before we start dividing by cosines and so forth, is to figure out what this value of c is. Since we have this initial condition, we can substitute in x equals 0 and y equals 1 in to try to find this constant of integration before we get too much farther. So I know that this should be cosine of 0 times 1 is equal to minus cosine of 0 over 2 plus c. Or better yet, 1 equals minus 1/2 plus c. c is 3/2. So substitute 3/2 in, we get cosine of x times y is equal to minus cosine of 2x over 2 plus 3 halves. Or solving for y by dividing everything by cosine, I get y is equal to minus cosine 2x plus 3, or how about 3 minus cosine of 2x. These already, I can do that because these have a common denominator as it was. 2, and then what I divided by, which is cosine of x.